as it pertains to harmonic motion, right? We have come to an understanding that whenever, because what you have to understand is that things do oscillate from time to time, right? Everything oscillates, meaning that it moves back and forth. Even your heart, the heartbeat, it's oscillating, it's moving back and forth. When you think about a swing song, it is oscillating. Now, hear me now. Let's imagine that we have an earthquake, right? Whenever an earthquake is, how can I say it, has occurred, right?
Wait,
Yes.
1 second, sir. Wait, there's something.
Are you
Yes,
back?
sir. Sorry about.
All right. Yes. So I was saying, whenever an earthquake is occurring, like it's shaking the earth and all of that. As you can see, it's a back and forth movement when something is shaking in an earthquake. Have you ever experienced an earthquake before? Hmm?
Yes, sir.
I didn't hear your answer. You said yes. What?
I said yes, sir. But it was just a slight one.
Okay. Right. So what we have come to understand is that whenever an earthquake is taking place, it's going to have what we call its natural frequency, meaning that it's going to oscillate back and forth. Now, whenever that frequency matches up with the frequency of a building, that is when the building is going to start shaking more rapidly, and would essentially cause some damage to the building. You feel me?
Yeah.
That process is what we call resonance. All right, is what we call resonance. Let's just put it to a video to just make life easier. Um, Resonance. Let's see if this explains it a little bit
To
better.
construct
Let me share the audio. Share audio. Let's see what he's going to say here.
the boss model, you're going to need one 24-inch length of two.
All right, he's going to just demonstrate something. I don't want that one. Give me a second here. Um,
When we see this kind of picture, it's a Mexico earthquake, we see that small buildings collapse and not high buildings. So it's a real problem. And what kind of problem is? It's a problem of resonance. So buildings resonance. So to understand this phenomenon, we can make this experiment with the same screwdriver, automatic electric screwdriver, with an eccentric here. And this system we can switch on, off, and also increase the speed. We have different building of different height, and I'm going to make the system working to show to understand what is the resonance phenomenon. So with this system, I can increase the speed and nothing appears because the eccentric is not far from the axe. So now I am putting this far, and now I see the beginning of the working, this system working. So now I'm going to study the resonance. We can see that the big buildings resonates. I'm increasing the speed. And now, yes, the big building, and now the intermediate building resonates. And I increase again, and I see the small building resonating too much and no foundation, so small buildings collapse. Maybe exactly like that, but it's not a problem of foundation. Here is a problem of size of building. So to change resonance frequency, it's possible to prevent resonance. To put a big mass on the building like that, and so the building does not resonate anymore, and I can search the new resonance because building is going to resonate, but in a low frequency like that. So the new frequency of resonance is this one. To prevent resonance, it's also possible to put a big mass, and the building resonates at low frequency. As you can see, the big mass is fixed, and the building has a big resonance. So now I'm going to make the mass free, in removing the scotch here. And when the mass is free, the system is an amortissement, and as you can see, the mass moves, but not the building. So it's the system which is used in Taipei Tower, and the computer are pushing the big mass to prevent the resonance of this building.
I hope you learned something. While it's not completely related to earthquake at the moment, but it's obviously related to resonance, right? So what you're essentially seeing is that the buildings have a particular frequency. Now, when the driving force or the force oscillation matches up with the frequency of the building, that is when it's going to oscillate much faster, and hence, what you would essentially see is that the building is moving faster, oscillating back and forth faster, and could potentially get damaged. So what you have to understand is that in the process of resonance, the amplitude of the oscillation rapidly increases, right? The amplitude will continue to increase until the system fails. So I don't know if you saw in the video where, different buildings were oscillating much faster at one point, and then when the frequency was increased to a different amount, the taller building stopped oscillating, and then the smaller one started picking up its oscillation. Let me know if you saw that part.
Yes, sir. I was about to ask you that. I expected the smaller buildings to oscillate more.
Okay. Yeah, so as I said, it depends on the natural frequency of the building, right? Depends on the natural.
So if you add more mass to it, it would help prevent it. Is that
Yes.
right?
It would help to prevent, yeah, it would help prevent it, yeah.
Okay.
So that's one way to we're going to learn another concept called damping very soon, and that is, I'll explain that, but it's important that you remember this graph, right? This is an amplitude versus frequency graph. Now, when resonance is occurring, right, you would expect that this part, if you're seeing a graph and they ask you to identify where the resonance is occurring, right, you can expect that it will obviously be where the amplitude is at the highest. You see me? So when the amplitude is at the highest, that is when resonance is occurring. And you can use the graph to find what we call the resonant frequency. The resonant frequency, right? So this is just when something is oscillating, and we say because you will see this happening in other scenarios. Like if you, you know, consider like a bridge. There's some bridge that oscillate when vehicles drive on it, and if if they're not careful in terms of the the amount of force that is being applied to the bridge by the cars driving on it, the bridge will oscillate back and forth and could potentially get damaged. You understand? So one of the things though, I was making mention of the earthquake, because if you get a question and it says talk about resonance, you can speak to earthquakes. So one of the things that you can do is to, because based on the values of the earthquake, we know in terms of the magnitudes, you know, you have different magnitudes of earthquakes, right? Up to about maybe 9, I don't remember, on the Richter scale. So what manufacturers or construction and engineers do is to ensure they can do two of one thing, or they can do two things to prevent the buildings from collapsing. They can either lower the resonant frequency of the building, right? So that if an earthquake should occur, chances are the frequency of the earthquake would be higher than the frequency of the building, so it would not cause it to damage. Or you could build a building with a very high natural frequency, so that when the earthquake occurs, it would not cause potential damage, because the frequency of the earthquake would not match up to that high frequency or to that natural frequency of the building.
Okay, so how would they do that? Like build it to a certain frequency?
Yes, so based on what he just showed us, right? So just as how we add the mass to the building a while ago, right? We see where that it altered the frequency of the building. So I guess based on the more mass that the building has, in a sense, that could potentially change the way how the building oscillates, right? And could lower the frequency. But there are other ways as well that you can use to prevent damage to the buildings, and that is going to be when we're going to talk about damping. And what you're going to see is that we can use springs in the building to pretty much prevent that oscillation, that rapid oscillation. So damping is going to be a method through which we can pretty much slow down the oscillation of the building by using springs and masses and all of that. I'll show you that eventually. But this is an experiment that we could have essentially do in the lab, where we would take a motor, right? And that motor is going to spin, and it's going to cause the string here to oscillate back and forth. But in the process of doing that, you're going to see that a spring that is attached to a mass is going to oscillate up and down. So based on the vibration that is coming from the motors, right? If the frequency is matching up with the frequency of the spring and the mass system, then it's going to have a very large amplitude, meaning that the spring is going to shoot all the way down and come back up and like that, you know? So that is just how we can actually simulate this in the lab. You see what I'm saying? So remember now that whatsoever frequency that you see the object moving in a very rapid way or having a very large amplitude, that is the frequency that we call the resonant frequency. You get me?
Yes, sir.
All right. All right. Is another way how we could do this as well, in terms of an experiment, right? Is by using what we call the Bartons pendulum, right? And what we have come to understand is that based on the length of the pendulum, right? If the lengths are the same, then when this driver, which is the one that is going to move back and forth, whenever this pendulum is oscillating, right? Any one of these that have the same length is going to oscillate because of the fact that this one is going to have a frequency that matches up to the frequency of the one that has the same length as well. And
Sir, can you please repeat that?
So here we have a pendulum, right? That is at a particular length. Now, when this pendulum is oscillating, right, this pendulum is going to cause another pendulum on this side to oscillate based on the fact that if the length of the next pendulum matches up with the length of the driving pendulum, then it's going to cause it to oscillate, you know, because we're seeing here that oscillation as well.
Okay, so
Go ahead.
So, sir, so you're saying that if an earthquake happens and happens at the same frequency of like any type of building, it could be like really large or small, as long as it matches, it would affect it more.
Yeah. Yes.
Okay, so if it's a small one, it would more affect the smaller buildings. If it's a large one, it would just affect the larger ones.
As we say, it works based on the natural frequencies of the buildings, right? So if the small buildings have a very high natural frequency, right, which is generally the case because those buildings they're shorter, so they don't oscillate back and forth very easily. So, but most times the earthquakes comes with very high frequency. So when that high frequency earthquake is shaking now, it will be more prone in some regards to damage to smaller buildings because those smaller buildings have a very high frequency or high natural frequency. With a tall buildings are designed to sway. I'm not sure if you know that, but they are actually designed to sway in natural scenarios. They're really designed to because the higher you go, you know, right? Wind and all of those things are going to blow the building, and from time to time it can move it. So to limit some of that movement as well is to pretty much incorporate what we're going to talk about, which is damping, right? To see that if the building sways too much, then the building is now designed with springs which would dampen the oscillation, which means it's going to kill the oscillation, right? So it's a lot, you know, it's a lot, and I can't tell you that I know everything about how it works, because you know these things are high level to some degree if you want to really know more about them. But from a small level, what we're saying here is that if I have a pendulum, right, and I realize that, well, not say I realize, but the fact of the matter is that this driver pendulum is going to cause the one that is at the same length to also oscillate. The other ones will not oscillate because it doesn't match up, you understand, in terms of the length. So this one right here is the one that would oscillate. And I saw this on a multiple choice, so I thought that it would be important for me to make mention of this. You know what I mean?
Okay.
Yeah. Right. So resonance is something that we use even on a daily basis too. Like, you know, there are good features about resonance. There's not only bad features about it, there are also good features. And one of this is when we deal with, you know, things such as ultrasound, scattering, right? Or mechanical resonance in a sense. Now, what happens in this process, and we must be able to think back about these to say that these are actually useful ways of using resonance. Now, in some medical procedures, right, you know, you might need to use resonance to actually break some type of bones that are actually growing inside of your body. Like maybe you have on your hand, maybe a piece of bone is kind of growing out on your hand. I don't, you know, like a small piece of spout or something of that nature, right? And you need to break that into pieces. You can use mechanical resonance, which essentially is coming from ultrasound. So you're using sound waves to travel with a particular frequency. Now, based on the frequency of the bone, which you can calculate in some mathematical ways, right? You can see that if I take the sound waves frequency and matches it up to the tiny bones that are growing in the body, you could actually break them apart and pretty much disintegrate it. So rather than using a surgery to cut it up or to cut off the bone, you can use ultrasound shattering, right, of tiny bones using mechanical resonance. Now, another way how resonance works is in the electrical, not electrical, but like when you're transmitting, you know, like signals from a radio station and television stations and so forth, even the internet, right? It uses electrical resonance in some regards, right? Let me see here. So like when you're tuning in your radio to Love FM or you know maybe Irie FM or Zip 103, what you're actually doing is that you are tuning into a frequency that the radio has. So the radio, right, using some electrical means, is producing a frequency, right? So when that frequency from the radio matches with the frequency of the radio station, that is when you actually hear the sound. You understand? So that is how we can also use resonance to pretty much you know get the transmission of sound waves to hear from the radio stations and all that crazy things, right? So it happens, you know, in real life. That's what happens there, you know.
Yeah. So the term electrical resonance, that's a correct term, right? Because I heard you said, well, not exactly electric.
No man, it's electrical resonance. Electrical resonance. Electrical resonance.
Okay.
Yeah. Yeah man, electrical resonance. All right. On the next slide. So there are several others, you know, like here are some more. Like when you think about MRI, like I'm sure you have heard about MRI, right? No, sir. Tell me.
Yes.
So it's actually using magnetic, some magnetic field, right? I'm not really sure as how it works mainly, but
I'm actually looking at it right now. It says that it's magnetic resonance imaging, as it's called.
yes, I know what it's called, but I'm saying um based on the terminology, you would expect that it probably would involve some magnetic field involved here, but we're not seeing that based on the explanation. So it says that it's used in diagnostic images of various parts of the body. Basically, radio frequencies are aimed at a desirable part of the body, and the amount of resonance occurs in hydrogen atoms is detected, which gives off a specific type of image. But I'm still wondering, why do they call it magnetic resonance? I'm trying to remember. I'm trying to see why they call it that. But at the end of the day, they're using some type of radio frequency to
They say that it uses a magnetic field and computer generated radio waves to create detailed images of the organs and tissues.
okay. Well, that's good, right? So make note of that as it pertains to it, you know. Now the last one is when we actually play certain musical instruments. Even a very guitar, right? A string instrument uses resonance. So when you hear a guitar making sounds by plucking the strings, it's actually using resonance. And not only that, when you consider a flute, you know a flute is a very hard instrument to play, right? Because you have to position your mouth over the opening and pretty much have a particular blow a particular frequency of sound inside of it, and with that it can resonate and create what we call stationary waves. Now we're going to talk about stationary waves because they are very important for us to understand further down. We're going to talk about those, but
Can you please repeat?
yeah, I was making mention of the flute, right? You would have to, when you blow in the flute, right? Based on the frequency of the air that is going inside of the flute, that can produce what we call um, standing waves, right? And we're going to talk about standing waves and see how it works further down, right? But what you must understand is that resonance is taking place in certain musical instruments, right? By way of sound waves, oscillating or moving back and forth inside of a particular tube. So we'll talk more about stationary waves or what we call standing waves further down the line. So these are the undesirable, effects, right? So see more information here as it pertains to it. So it says that earthquakes occur at very low frequencies. So I think I can correct myself now because I did say that the earthquake. Well, I had said it can occur at several different frequencies, but in this it's saying that it occurs at very low frequencies. Now it says that tall buildings and large bridges also sway at low frequencies naturally. It says that one of the reasons why bridges and tall and heavy buildings collapse during earthquake after whereas shorter buildings do not is due to resonance. It says that um, when the frequency of the energy supplied either by the earthquake waves, water waves, or a gust of wind matches the natural frequency of the structure, resonance occurs and the structure vibrates at large amplitudes, often with resulting damage. So I was correct when I was talking. Go ahead.
But in the experiment shown, right?
Hmm.
It's we did see some swaying with the larger buildings, but the smaller ones were affected more.
Yes,
So
because no, the reason why those smaller ones were affected more was based on the high frequency. Because it says here that smaller buildings, right, generally have.
yeah, but earthquakes, it says that earthquakes also occur at low frequencies.
So hold on, no, if you look at it back in the camera, hold on, no. You see, if we look back at it, we can see where the frequency of the oscillation that caused the small buildings to collapse, right, was based on a high frequency. Because that, I don't know if you saw it, but like the building behind, like the small building behind, it was moving rapidly, and that was because of the fact that the drill was oscillating really fast, which means that frequency was very very high, right? So small buildings have a very high
Okay.
frequency, right? Whereas we say that taller buildings have a lower frequency. That was the reason why you would have seen the smaller buildings, the taller buildings oscillating first. So let's look back at it. Let's look back at it.
Electric screwdriver with an eccentric here. And this system we can switch on off and also increase the different height. Understand what is speed and nothing appears because the eccentric is not far from the axe. So now I am putting this far and now I see.
All right, so I don't know if you saw that, but you can see that the taller buildings they're oscillating. Are you seeing that?
The beginning of the working this.
So the taller buildings are oscillating more than the smaller ones. Cool?
This system working. So now I'm going to study the resonance. We can see that the big buildings resonates. I'm increasing the speed. And now, yes, the big building, and now the intermediate building resonates. And I increase again, and I see the small building resonating too much.
Right? So with that, it shows us that the taller buildings resonate at low frequency versus the shorter buildings. They resonate at relatively high frequencies. You see what I'm saying?
Yes.
Mm-hmm. right? So yeah, so these are the main things. This is just a talking about another thing. I made mention of this already, but when people travel across a bridge, right? Um, will provide a driving force, right, which will equal to the natural frequency, which will cause oscillation or large oscillation due to resonance, right? These oscillations are potentially damaging, are very dangerous to the building, right, and could lead to some damage. And also in aircraft, like some parts from an aircraft can get damaged due to resonance. As you know, the plane is traveling through the wind, right, or through the air. Now, if that wind or that air particle is matching up with some natural frequency of some parts on the engine or some parts on the airplane, then chances are it's going to vibrate and will possibly break off. You understand? So we looked at desirable effects, and we are now looking at undesirable effects of resonance. So we ought to be able to can explain a few of these, have a little bit of knowledge on how these things work, what resonance really is, right? Those are important for us to make mention of. And the graph that I showed you just now, it's a critical graph. We must be able to can draw that graph, or even to, if we see it in the future, we know that that is the graph and know where to identify the resonant frequency. You follow me? Okay. Now, remember I've been making mention of a concept of damping, right? This is what damping is. So remember we said now that in resonance, the amplitude is very high. Good. So one way in which we can reduce that amplitude or that oscillation is to go through a process of damping. So damping is that process by which the amplitude of the oscillation decreases over time. Now it says that this is due to energy lost to resistive force, such as a drag force or friction. So over time, that building that is oscillating, it potentially can stop oscillating because of the resistive forces in the atmosphere. So air is going to slow it down. Nothing will oscillate. If you think about a pendulum, if you were to make a pendulum move back and forth, right, it's going to stop at some point, and that is just because energy is being lost because of the resistive force and friction force in the atmosphere. You understand me? Also with a spring, right? That is going to also happen. So yeah, but as you can see right now, you're seeing some graphs over here. Those graphs are critical graphs for us to note. We have to know these graphs and the reason why we have them, right? Let's look at it in greater details. All right. So obviously, the first graph that you're seeing here is a graph that does not involve any damping, right? That's just a typical oscillating graph, right? It doesn't show that there's any damping. Now, when you look at the second graph now is showing what we call underdamp or underdamping, and it tells us what underdamp means, or what it speaks to. So it says that the amplitude of the oscillating object decrease with the passage of time, and it says as the object makes several oscillations. So it's going to decrease. So the amplitude is going to decrease over time, and it's going to make several oscillations back and forth until it dies out. Another terminology that you can use for underdamping is what we call light damping, right? And that mainly occurs when you have like a pendulum moving back and forth through the air. So that is what happens. Now, there's another type of damping, what we call critical damp, right? Now it says that the graph of an oscillating object reaches the equilibrium position in the shortest possible time and remaining in that position, right? This kind of damping is called critical damping, and it says that the object stops before one oscillation. So this is a very important feature of damping to us, because we're going to look at some examples of when we are using damping, and you're going to see how it makes sense, right? Because there are times when we don't want something to oscillate back and forth. So the best thing is to critically damp the scenario. And when you do that, you're essentially trying to allow that object to come to a stop or come to rest in the shortest possible time. You know? So that's what critical damping is. And so this is what the graph looks like for critically damp on this one. Right, this one right here. As you can see, there's no oscillation. Oscillation would involve going up and down. It just comes right down to zero, right? So that's what critical damping looks like. Now, for lightly damped, you're seeing that the graph is decreasing over time. There's another type of damping, what we call heavy damping. That is sort of a more drastic damping versus when you look at light damping. You will see oscillation taking place. Go ahead.
How will they achieve it?
How do they achieve it? Well, so springs mainly are used to perform this type of damping scenario, right? Because what we're going to look at, and even fluids, there are certain fluids that can help with the damping process, right? Yeah, but mainly springs though. So, like when you think about a car, right? When you think about a car, I do wonder sometimes how is it done completely, right? But when you think about cars, now imagine if you never have what we call shock absorbers in a car, when you drop in a one pothole, right? That car would be bouncing from now until tomorrow morning. So what engineers have done is to design the system in such a way that the suspension, right, is able to go to a process of critically damping very quickly so that you don't get a bumpy ride. You see what I mean? So
Yes, sir.
in the shock absorber, right, they incorporate certain fluids that are there, you know, to it's a whole other engineering process, right? I mean, it's so much, but they know how they did it. I mean, it's not easy to explain, but just know that that is one application, right, where critical damping comes into play, because you don't want the vehicle to be oscillating back and forth very quickly or rapidly when you drop in a pothole. So you need a system that can right away damp it so that it does not experience a lot of oscillation, right? Or matter of fact, no oscillation at all, because critical damping does not oscillate. There's no oscillation. It just go right back down to zero. All right, I have less than a minute, so I'll restart it and you'll rejoin. All right.
Okay.
Yes. So another way how, let me just go back here a little bit. I should have explained. This thing is a little bit tricky. Okay. I'm wondering if I had, but either way, overdamp, right? Overdamp is another type of damping process, right? Where we can see that, you know, firstly, the object does not oscillate any at all, right? but what it takes a much longer time for it to reach back to its equilibrium position, or reach back to zero. So that's what happened in over damping. So no oscillation occurs in over damping, right? But it just takes a much longer time for it to reach to back to the equilibrium point. As in regards to damping again, another application of critical damping on a whole, right, is um is used whenever we're looking at a speedometer, right? So it's obviously important that we damp a speedometer, because if the needle is oscillating back and forth, right, what can happen is it could give the reader a very incorrect reading. So what if you're driving your car and you see the speedometer, oscillating back and forth? It's going to throw you off. You're not going to be able to get an accurate reading. And I think I can show you what I mean by that. Hopefully I can find something here, I mean. I know at one point I saw something. But let's just look at critical damping and see. So yeah, they're not showing. I know I saw it one time. I saw something pertaining to a speedometer moving back and forth. Oh yeah, yeah. Give me a second. All right, so I'm not finding that, but yeah. What you have to understand is that if the speedometer does not go through a process of damping, right, you would just see the needle moving back and forth, and you would not know what exactly you're reading or where the pointer is at. You understand?
Yeah.
All right. Now, as it pertains to heavy damping, it happens and we don't know that it happens. So like when you go to like, like leave like a Mall of America, or um maybe you go to like Western Union, well, not necessarily Western Union, but you go somewhere that uses some, the door, when you open the door, you realize that the door closes by itself and it takes a much longer time for it to close. That is just as a result of heavy damping, right? In most cases, some of those doors, like you have some doors that can oscillate back and forth, meaning that once you push through it, it goes in and out, you know. But what we're seeing here, to prevent that from happening, you can use a pretty much a spring system in a sense to dampen the heavy damp the door so that it does not swing back and forth, to probably hit somebody and all of that, or even to slam, you know. But also it is used to actually close back the door as well, right, to keep the air conditioning in and all of that. So that's like a application of that type of damping, right? I'm not sure if we went through some of these questions, but these questions would have been related to the whole you know, can I say simple harmonic motion, calculating the different frequencies and so forth. I don't know if we did go through these questions. Are you still there?
Yes, sir. I'm listening.
Yeah, I'm wondering though if we did go through these questions. That's what I'm wondering. If we go through any of these questions.
Sorry, it looks familiar.
All right. So one of these questions says that a particle is oscillating in simple harmonic motion with a period of 4.5 milliseconds and amplitude 4 centimeters at time equal t equals 0. The particle is at equilibrium position. It says calculate for this particle the frequency. Then they go and ask us to calculate the angular frequency. Then they go and ask us to calculate the maximum speed. Then they go and ask us to calculate the magnitude of the maximum acceleration, and they then ask us to calculate the speed at time equal 1 milliseconds, right? Now, based on this question, how do you think we're going to find the frequency?
Pardon?
Go again?
What was that, sir?
How would you find the frequency here?
Okay, to find the frequency, I'm not sure. Are we going to be using this oscillation with the amplitude?
I'm listening. All right, look at the question.
What was that, sir?
Read the information and see what do we have, and then we can see how we could possibly find the frequency, right?
Okay, so the oscillation particle. Okay, the oscillation of the particle with a period of 4.5 milliseconds and amplitude at 3 centimeters and time 0. So the frequency would be would it
Say it again. I didn't hear you. Yeah, you're breaking up.
Okay, so the frequency would be the time, which is a period given, which is 4.5 milliseconds, with the amount of time it occurs.
What's the formula we're going to use?
So it would be like the amount of times it occurs divided by the length of the time.
No.
No?
Hold on. You might not be incorrect about that, right? So frequency is the number of oscillations per unit time, right? But in this regard here, right, we don't know the number of oscillations. You see what I mean? So we can't
Oh, yes.
use that, right? What we're going to use is this, and I'm pretty sure you know this. Frequency is equal to 1 divided by T. Is this the first time you're seeing this?
No.
Yeah, so this is what we would essentially use. So we know the period. So it means that we can find the frequency, which is going to be 1 divided by 4.5 times 10 to the minus 3 seconds. So when we do divide this, 1 divided by 4.5 e to the minus 3, we're getting that the frequency is going to be 222.2 hertz, right? So that's that.
Okay, so we use this when we don't know the amount of time it happens.
Could you say this again?
So we use this formula when we don't know the amount of time it happens. I mean,
the number of oscillations.
Can I still use it the way I just explained?
So that you'd have to know several things. I mean, you'd have to know the number of oscillations and the time taken to complete those number of oscillations, right? So because you don't have all of that, then this is what you'd have to use, if you get me.
Is that 222.2 hertz?
Yes.
Okay.
So the next part of the question asks us to find the angular frequency. How do you think we're going to find the angular frequency?
I'm not sure, sir. Wait, so angular frequency would be 2 pi upon the.
Say it again.
Upon the. So that's T.
Yes, so we could have done it this way, right? This is one formula. So angular frequency, which is omega. So omega is that symbol, almost like a W, right? Let me erase it and write it back over. So omega, which is what we call the angular frequency, is equal to 2 pi divided by T, or you could say 2 pi, right, times F, which is the frequency. So there are two ways you can do it. So let's go ahead, take our frequency, which is 222.2 times 2 times pi. That's going to give us a omega value of 1396, and this unit is going to be in rads per second. Rads per second.
Yes, sir. You did give this problem already.
Okay, good. Then now for the maximum speed, what are we saying for the maximum speed? If we did it already, then I guess you should have the answer for the maximum speed, right?
No.
All right, so to find the maximum speed, V is going to be equal to omega times the amplitude, all right? Omega times the amplitude. So now that you know omega, which is your angular frequency, which is 1,396, you're going to multiply that by your amplitude, which is in centimeters, which means that you need to convert it into meters. So that's going to be 3 times 10 to the minus 2. When you work this out now, we are getting a value to say that our angular or maximum speed rather is going to be 41.88 meters per second. Right?
What is that?
What is what?
The answer you have here for something?
Yeah, 41.88 meters per second. Now for the amplitude of the maximum acceleration, right? This is going to be A is equal to omega squared times the amplitude, right? And we know omega already, so we're saying that 1,396 squared times the amplitude, which is 3 times 10 to the minus 2. Or acceleration is going to be 58,440 6.5 meters per second squared.
Wait, so can you please repeat that number? So 58,464.5.
Yes. And then it then asks us to find the speed, right? At time t equals 1 millisecond. This one is going to be a little bit tricky because I have to do this first. Let me try this. Right. First, the question said that the oscillation started at equilibrium. So this is how the oscillation is taking place from a displacement standpoint, where your amplitude is right here, the negative amplitude is here. Now we have to recall something here as it pertains to the speed. Now, I believe the speed at the equilibrium is going to start here. Would it be here or down here? Yeah, I believe it's going to start here. It's going to start at the amplitude. So the speed would start at the amplitude. So as it relates to the speed graph, right, it should look something like this.
So continue to do this to find the speed
No,
at a certain.
not necessarily as yet. We just need to establish something first because I'm going to skip back and see if this is what we're supposed to have. But at the end of the day, we must know where the graph is going to start for our speed, when the particle starts at equilibrium position. I believe that it's going to start at the amplitude, right, in terms of the speed, maximum speed. But I want to be sure if it's going to be positive or negative. So I'm going to skip back and see whether if it's positive or yes. So I was correct, right? So this is the graph that we're talking about, right? This is the graph that we're making reference to. Seeing that the particle started at 0 and had a positive amplitude, then it is taking, it's going to be a sine graph, right? Now, this one now, it starts obviously in the positive amplitude. Go ahead.
Asking if you can please
You're kind of breaking up,
explain. You were explaining why
Okay.
sine.
Yeah. So sine, whenever the particle starts from equilibrium position, right? Then it's going to have a sine graph in terms of its displacement versus time. Good? Now, whenever something starts at equilibrium, the velocity versus time graph is going to be a cost graph. Cost graph starts at the amplitude. Good? So sine graph starts at equilibrium position. Cost graph starts at the amplitude. And we're seeing here, this is what the velocity graph looks like. So when I go back around here now, right, I know for a fact that this equation for finding my maximum, well, not the maximum speed, but finding the speed in general, it has to come from this equation that says V is equal to, you could say V naught. V naught would represent the maximum speed, right, times cost of omega t, right? So I will have to do some calculations now to pretty much find the speed when time is equal to t. By the way, there's another way we can write this equation. We could say that v is equal to omega times the amplitude times cos omega t. So if I go ahead, I would have calculated the maximum speed already, which is 41.88, right? So having said that, I would have calculated the angular frequency as well. Now this is the part that gets a little bit tricky because we have to do some calculations and we have to make some convergence from rads to seconds mainly, right? Not seconds, but degrees rather, right? So, all right, let me see here. 360. So whenever we're completing a circle, right? Whenever you have a circle, this is already made mention in lessons, so you just need to probably just watch those and see what we're saying here. But 360 degrees is when you complete a circle. In terms of radians, that's going to be 2 pi radians. Now I want to know what does 1 radians represent. 1 radians is going to be equal to 180, right, divided by pi. So 1 rad is equal to this. And I'm going to show you where this is going to come into play. So in order for me to find the speed, right, this is what I'm going to do. So V is equal to the maximum speed, which is 41.88 times cos. Now, I need to put in the angular frequency, which is 139.6, right? But now is when I have to convert from radians to degrees. So right here, that where we have rads, I have to convert rads into degrees, and 1 rad is equal to 180 divided by pi. I have to do that because I'm going to work my calculation in degrees, and I have to convert it over from radians using this particular information. Now they told us that the time is 1 times 10 to the minus 3 seconds. So now what I'm going to do first, I'm going to work out this part first, just to get it out of the way, right? So I could work in the bracket first. I can take 1,396 and I'm going to multiply that by 180. Then I'm going to divide that by pi. When I do that, I'm getting that cost of 79,984.3. Now let me try costing that number and see what I'm going to get. When I cost that number, right, I get a value that says 0.4241. So what I'm going to do now, I'm going to go back and say, all right, V is equal to 41.88 times 0.4241 times 10 to the minus 3. So I'm getting that V is equal to 0.015 meters per second. I don't know how true this is, but that is what I'm getting. I don't know if we made any errors. I don't think we did make any errors. Right? So.
Okay, so.
Yeah. That would have been the speed. Let me just try something here. Give me a second. 2 pi divided by 4.5 e to the minus 3. Yeah, I think it's correct. Right. So yeah, that would cover that. You know.